announce today the next speaker, Professor Huyên Pham, who is a full professor at the University of Paris Diderot, and who has a number of very seminal contributions. In particular, he's the author of this well-known book on continuous time control problems, with applications also in finance. And in the recent years, he made also very significant progress on machine learning methods for approximatively solving partial differential equations and optimal control problems. And that's also where his talk is today about. And yeah, with these words, I would welcome very much Huyên and look very much forward to your talk.
Okay, so thank you, Arnold, for the introduction. Thanks to the organizer for inviting me and giving me the opportunity to present my talk today. So I think I should share my screen now. Okay, can you see my screen?
Yes, looks
okay.
good.
Yes, you can see.
Okay, thank you. Okay, so so my talk today, so it's about the numerical method for solving a mean field PDE. Okay, by using techniques from machine learning, deep learning, and so it is based on a joint work. So actually, it's still a work in progress. So with Maximilien Germain, who is a PhD student of mine that I co-supervise with Xavier Varin from EDF, and it is also joint with Mathieu Laurière from Orphée in Princeton. Okay, so the outline of this talk is the following. So first, I will describe the problem we are interested in, and giving some motivation. And so, as you will see, so the PD we intend to solve, so it's a PD in 5 dimensions, so more precisely in the space of probability measure. And so in the second step, I will provide the 5-dimensional approximation of this PD by means of particle methods. And notably, I will show the rate of convergence that we can obtain for approximating this PD. And then the second part of the talk, okay, will be devoted to the numerical scheme. So, and for that purpose, I will introduce a set of neural network called symmetric neural network that have been introduced, quite recently in the machine learning community in order to handle with tasks that involve data set which possess some invariant structure and which arise, for example, when you deal with point cloud or in cosmology or quantum mechanics. And we shall see how it is quite helpful when handling with our PD, mean field PD. Okay, and finally, I will give some the algorithm, okay, for solving our PD, and that I will illustrate with some numerical example. Okay, so the PD, okay, we are interested in, so it's a parabolic PD, so it involves the time derivative. So it's a PD on the Wasserstein space of probability measure, square integral probability measure. So as a PD, so it involves a partial derivative with respect to measure. And so, so for our purpose, so we shall use a notion of L derivative. So L, capital L derivative mean lifted derivative. So it's a notion of derivatives that have been introduced by Pierre Williams in his lecture at Collège de France. So there are different, of course, there are different definition of derivative respect to probability measure. Okay, but it is now known that they are more or less all equivalent, and here it's convenient to use this notion of probability measure. So for this talk, all you need to know, okay, is simply the fact that if you look at this partial derivative, so of a function with respect to a measure, so at a given point, it is a function from Rd into Rd. And so as a function from Rd into Rd, okay, you can consider its cross derivative. So it's a partial derivative with respect to the standard x argument. So that I will denote by partial x, partial mu, and which is then a function from Rd into the set of D times D matrices. Okay, and I call this a mean field PD because the Hamiltonian H, which occurs in this PD, okay, has a special form. So it is under expectation form, which means that this function H, okay, is integral of some function small h, where you take the integral with respect to the probability measure mu. Okay, and recall that the argument for the partial mu and partial x partial mu are functions, so you integrate with respect to x here. Okay, and so this small h, okay, we call the integrand Hamiltonian. Okay, so what is the motivation for studying this such kind of PD? So it's in fact motivated by mean field problem, and more precisely by problem when you have a large population of interacting agents. Okay, and so usually you may distinguish two types of interaction between the agents. So the agents can be either under competition, so they act in a strategic way, and so typically you are looking from some consensus, so in other words, a Nash equilibrium, or these agents, okay, can be cooperative, so meaning that they obey to some social planners aiming to minimize some social cost. And when you look at the asymptotic regime, when the number of agents capital N goes to infinity, okay, you will fall into the theory of mean field games, okay, or mean field type control, so also called Makin-Brazov control problem. So such a problem has attracted over the last decade a number of great interest, okay, since the pioneering papers by Lastry and Lyons, and independently by Huang, Malem, and Keynes. And they also generated many and various applications, okay, in different topics ranging from economics, finance, population dynamics, and more recently in social science, where you have very insightful application, typically in opinion dynamics in the context of elections. So back to our problem, if you look at the PDs that I presented in my previous slides, in fact, it represents typically a master equation if you are in the context of Milfin game, or a Bellman equation when you are when you deal with Makin-Brazov control problem. And so it's a partial differential equation in the Wasserstein space, which has been extensively studied over the last year, both in I would say in the deterministic community, also numerical analysis community, or in the probabilistic community. So here I just mentioned some papers, but it's not exhaustive, and I apologize by advance if I could not put all the contributions. But okay, so in fact, in this talk, so we are more interested, in fact, in the numerical approximation. So in other words, we aim to find a numerical approximation of the solution to this PD, but also possibly of its lifted derivative. Okay, and for that purpose, okay, we would like to develop a machine deep learning methodology. Indeed, it is now known that this machine learning method have provide a breakthrough for solving PD in 5 dimensions, and they allow, in fact, now to solve PD in quite a very high dimension. And so over the last 5 years, there were many important contributions. So, of course, Arnaud Jensen, Weinan He are pioneer in this field. I would like also to mention the deep Galerkin method, and I also provide some contribution to this area. And so the basic goal of this work is to see how one can extend or develop this methodology to our infinite dimensional setting when we have PD in the space of probability measure. So let me mention that, of course, we are not the first one who are interested in this topic, and so I have to mention some recent papers, okay, in this direction, done by René Carmona and Mathieu Laurière, and also recently by Lars Rustoto, Stanley Osher, and their co-authors, but okay, with a different method. So before presenting our approach, let me maybe recall. Okay, just in a nutshell. Okay, what is the essence of machine learning techniques when you want to solve PD in 5 dimensions? So suppose that you have some PD. Okay, so define parabolic PD. So define some domain space. So typically 0t times RD. And so the aim is to approximate V and also its derivative, in fact, by neural network, so more or less deep, so depending on the number of hidden layers. So in other words, okay, you want to approximate the solution and its gradient, okay, in terms of some class of function, some parametric class of function, where the parameters, okay, are related to the architecture of the neural network. So in other words, the number of hidden layers and the neurons. Okay, and so machine learning means that, okay, you will have to learn, okay, the optimal parameters, and so the learning is achieved by minimizing some loss function, okay, so usually by a stochastic gradient descent algorithm or some variants like the Adam optimizer, which have been popularized and implemented, for example, on TensorFlow. And these algorithms are based on some training simulation on the domain space, which represents the input data. Okay, and the different scheme that we can find okay, in the literature, in fact, will differ according to the choice on one hand of the loss function. Okay, and so the loss function may be either global or local, and also of the approach, okay, which is used to define the loss function. So the approach may be deterministic or probabilistic, or more precisely based on backwards differential equation. And in this table, okay, I try to classify the different method, okay, according to the approach and to the optimization. Okay, and on the other hand, okay, the scheme will also differ according to how you will simulate, okay, your training data, okay, and this is relating to the issue of exploitation. Okay, so now let me start by describing our approach. So the first term, which is of course quite natural, okay, is to reduce, okay, the initial problem, which is a problem on infinite dimension, okay, to a problem in a finite dimension. And so the simple idea, in fact, is to look at the PD, okay, which is not on the whole space of probability measure, but on the we look at on discrete probability measure, okay, supported by endpoints, okay, and more precisely to probability measure which are in fact empirical measure, okay, supported by endpoints, okay, in RD times n. Okay, and then you look at the PD, okay, restricted at this empirical measure, and so this define a function Vn, okay, which is now a function Vn defined on the supporting point of this probability measure. So it can be viewed as a function on Rd times n, and then okay, using the relation, the derivative relation between the function view as a function on RDMs or the function on the space of probability measure, so which has been derived, for example, in the paper by Chassagner, Krizan, and Delaru. Okay, so you have this relation between this derivative, okay, and plugging this derivative into the PDE, okay, and neglecting the term in 1 over n2 square, so this last term here, okay, then you will obtain in fact this 5-dimensional PDE, okay. So of course you have this 1 over n for the sum, okay, which approximates this empirical, the expectation form of the Hamiltonian. And the peculiarity of this PDE is that if you look at the dependence on the gradient, okay, you have this factor n here, okay, which comes from the fact that you have this 1 over n, okay, in this derivative. Okay, so this is now you have a PD in 5 dimensions, so in Rd times n. Okay, and of course you want to justify that such PD indeed provide a correct approximation of your in 5-dimensional PD, and actually it has been recently proved, okay, in a paper by Gangbo, Mayorga, and Zviech, okay. In the semilinear case, so I will precise what I mean by semilinear PD case, and also with common noise. So they prove, in fact, that the solution Vn to this 5-dimensional PD, okay, will converge, okay, to the solution to the original PD, okay, and so the arguments are based on viscosity solution arguments. And so in this work, so we shall provide an alternative proof of this result, but rather using a probabilistic arguments. And furthermore, okay, we would, as we shall see in a moment, okay, we would be able, in fact, to not only prove the convergence, but also to obtain a rate of convergence, okay, for the convergence of Vn to V, but not only Vn to V, but also its derivatives, okay, which is also a powerful way when you deal with probabilistic arguments. Okay, and so as I say, okay, we, as in the paper by Gangbo and Zviech, okay, we shall prove this result in the semilinear case. So by semilinear case, I mean the case where the dependence on the PD, okay, is a linear with respect to the second order derivative, okay, and the nonlinearity, okay, occurs on the first order derivative, okay. Okay, so this means that, okay, it's linear in the Hessian, okay, and nonlinear in the solution and its a gradient. Okay, and so in this case, okay, we can, okay, rewrite the PD in this form. Okay, so we separate, okay, the linear part, which is here, and the nonlinear part, okay, which is present here with the Hamiltonian edge. And notice that I have introduced an auxiliary coefficient B here, okay, in front of this gradient. And so because I introduced this auxiliary coefficient B, okay, I need to subtract from the Hamiltonian edge, okay, in these terms. Okay, so we shall see in a moment the role of this coefficient B. So in theory, okay, you can simply take B equal to 0. But in fact, B is mostly motivated, introduced here for numerical purpose, because in fact it is related to the drift of your training simulation. And it's quite important, okay, when you want to approximate correctly your functions, because in this case, okay, you will simulate, okay, based on this drift, and it should be chosen in practice to explore well the space of interest. Okay, so if you look at the linear part of this PD, okay, you recognize in fact, okay, the generator, the infinitesimal generator of a diffusion process, and in fact more precisely of a particle diffusion process, because here you see the dependence on the empirical measure. Okay, so and indeed, okay, if you look at this linear part of this PD, okay, it is naturally connected, okay, to an n particle system. Okay, so which is written here. So it's so n particle system. So it's you have n stochastic differential equations. So each driven by independent Brownian motion. Okay, so it's interacting because in the coefficient of the drift and of the coefficient, okay, it involves, okay, the empirical measure of the systems. Okay, and it's this particle system is connected to mean field SD in the regime where you send the number of particles to infinity, and this is a well-known propagation of chaos. Okay, which basically says that when n goes to infinity, okay, the law of this particle system converge to Macklin or mean field SD, okay, driven by this Macklin-Vazov system, where here this notation P of xt means the marginal law of xt. So it's a mean field SD where the coefficient depends not only on x but also on its marginal distribution. Okay, so this is the convergence of the empirical measure, okay, to its theoretical distribution. Okay, so this is so this forward system, okay, is related to the linear part of the PD, and in order to deal with the nonlinear part of the PD, okay, we shall rely on the probabilistic representation, okay, due to the seminal paper by Pardue and Peng. Okay, so and which is formulated by this equation. So what is the meaning of this equation? So you start from the forward system, the forward particle system Xn, and then you look for a pair solution, so Yn and Zn. Okay, so Zn is the integrand, okay, of the stochastic integral with respect to each of the Brownian motion Wi. And so the meaning of this BSD is that you look for the pair Yn and Zn, so that at the end, okay, you match, okay, the terminal condition of your PD, okay, and taking into account, okay, the nonlinearity of the PD, okay, through this Hamiltonian term H. Okay, and this probabilistic representation is related to the to the PD Vn, okay, by this relation, so which says that in fact the solution to this BSD Yn, okay, is in fact equal to the solution to the PD, okay, evaluated, okay, along the forward particle system, okay, and the component Z, okay, which in this BSD, okay, should be understood in fact as a gradient, okay, of the solution to the PD, okay, the gradient with respect to xi, okay, at least when the solution to the PD is smooth. Okay, so this is okay, so you really have to see this BSD representation as an extension of the Feynman-Kac formula for linear PD. And so now this means that, okay, you can express the solution to your PD, okay, in terms of the yn and zn, okay. And so now if you want to evaluate the errors with respect to the original PD, okay, then you can define this following pathwise error. Okay, first on the solution to the PD. So in other words, you define the difference between YTN and the solution to the PD, okay, evaluated along the empirical measure. Okay, and you define also the error on the lifted derivative, okay, by this relation. So it's okay, so it's the L2 square error, okay, between NZI, okay, where ZI is the solution to the PD, minus, okay, the Lyon's derivative, okay, evaluated along the system of particles. Okay, and so, okay, in order to prove, and so now the aim is to prove the convergence and the rate of convergence of this pathwise error. And for this, we need to make some assumption. Okay, so in fact, two kinds of conditions. So the first condition is a rather strong conditions. Okay, so it says that, okay, there exists a smooth solution to the PD. Okay, so which is of course a strong solution, but okay, there exists. Of course, in general it's not true that we can find a smooth solution, but at least in some example, it's now we know that we can find a smooth solution to the PD, and so we assume the existence of a regular solution to the PD, satisfying some linear growth condition. And the second type of condition is this time rather standard. So it's essentially says that okay, that the BSD which represents the PD is well posed. Okay, so in other words, we assume that the coefficients which appear in the PD are Lipschitz or locally Lipschitz, and that the diffusion coefficient sigma is bounded. Okay, and so under this two assumptions, here is our main theoretical result. And so the result is that, in fact, the convergence of the approximation of the solution and its gradient, okay, by means of the particle system with n particles, okay, converge with a rate 1/n. Okay, and so this is the rate of convergence. So it's a rate 1/n. And so let me just give just a sketch of the proof. So the proof, in fact, is based on an Ito's formula applied to the solution to the original PD, okay, but evaluated along the empirical measure. And so this is why here we need to have a smooth solution to apply Ito's formula and use the chain rules for solution defined the space of probability measure. And then you need to compare with the solution to the 5-dimensional BSD. And so the comparison is obtained by linearization arguments for BSD and change of probability measure techniques, okay, in order to overcome the nonlinear dependence of the generator H, okay, on the gradient, which is multiplied in fact by the capital N. Okay, so this is the essential technical difficulty. And so using a comparison argument, so then you would obtain an estimate, a pathwise estimate on the solution V. And then in order to get an estimate on the gradient, okay, the trick, which is rather standard for people familiar with BSD technique, okay, is this time to apply Ito's formula to the square. Because when you apply Ito's formula to the square, okay, you make appear, in fact, the gradient term. Okay, and then at the end, okay, you would obtain this rate of convergence 1/n. Okay, so now that we have proved the convergence, and in fact the rate of convergence of this finite dimension approximation, and in fact of its BSD representation. So now we have in principle, okay, a methodology to for applying, okay, the various machine learning schemes, the different machine learning schemes that have been designed for solving PD in 5 dimensions. Okay, but of course here we need to recall that also our PD is in 5 dimensions. It is still, of course, a very high dimension, because now the dimension is of dimension d times capital N, where N is the number of particles. So typically in practice, N may be, for example, equal to 1000. Okay, so also now we know that the method of machine learning can be very efficient in high dimension. Still here we are in very, very high dimension. And so rather than adapting directly the method of machine learning, in fact, we shall, the new idea, in fact, the trick is to exploit the symmetry property of the particle system, in fact, to obtain better accuracy of the deep learning network techniques. Okay, and so let me now precise what I mean by a symmetry property of the PDE. And for this, okay, so I will start by recalling what we call by a symmetric function. So a symmetric function, okay, is simply a function which is invariant by a permutation of its arguments. Okay, and so typically you may think about the max function, which is of course exchangeable function, or also the sum or average function. Okay, and so what we can show rather easily is, and not surprisingly, is that if you look at the solution to the PD, okay, to the PD, to the 5-dimensional PD, okay, obtained from the particle approximation, then this function Vn is symmetric. It is exchangeable, okay, on one hand, and on the other hand, you also have this structural property on the gradient of this exchangeable function. Okay, so in principle, when you want to compute the gradient of Vn, so you need to compute the gradient with respect to each of the arguments xi. Okay, so it means that you have in principle n function, n gradient function to compute, but in fact, exploiting the fact that it is de-exchangeable, that the function Vn is exchangeable, then in fact, it turns out that if you look at its gradients, it can be in fact simply represented uniquely in terms of a single function that we call a de-exchangeable. So what is a de-exchangeable function? So it is a function which is exchangeable with respect to these n first arguments. Okay, and so the gradient with respect to xi is equal to this de-exchangeable function evaluated at xi. Okay, and as we shall see in a moment, it's quite useful because now when you want to approximate, okay, this gradient, okay, you will need only to approximate, okay, this de-exchangeable function. Okay, and so now that we have this symmetry property, and so this motivates us, in fact, to introduce, okay, a class of symmetric neural network, okay, in order to approximate both this function Vn and its gradient. Okay, and so for this, okay, we shall use a symmetric neural network. And before defining what is a symmetric neural network, so it will be based on feed-forward neural network. So I guess now most of you are now familiar with what is a feed-forward network. So let me just give this now very classical picture or architecture of a feed-forward neural network. So it's defined in terms of hidden layers, okay, which represent the input okay, and the number of neurons is the dimension of your function, of your entry function. Then the output layer, okay, is composed of D prime neurons, and between the input and output, you have hidden layers. And feed forward means that each neurons, okay, it connected to the neurons of the previous layers, okay, by affine maps together with a nonlinear function. Okay, and so the important property from practical and theoretical point of view is the fact that you have the approximation capability of this of the sequence of neural network. Okay, when you increase the number of units or neuron, okay, in the hidden layers. Okay, so now that we have, I recall what is a fit for neural network. Okay, so we can now, okay, introduce what is a symmetric neural networks. Okay, so a symmetric neural network is actually constructed, is built, in fact, in terms of two feed-forward neural network plus symmetric operations. Okay, and so maybe you can go directly to this picture here. Okay, so you have your input. Okay, so say your particles, so which n particles, each particle xi, okay, is of dimension d. Okay, and then you apply component-wise a feed-forward neural network phi. Okay, so you get phi of xi, phi of x1, xn. Okay, and each phi is of dimension k. And then, okay, you apply a symmetric operation. Okay, so applying a symmetric operations, okay, you go back to Rk, dimension k, and then you apply a second feed-forward network psi. Okay, and so you see that there is an additional parameter k, okay, which is the dimension of the first feed-forward network. And so k, in fact, it's in the original symmetric neural network represents the number of features which describe the geometry of the set. And in our context of mean field problem, you may typically think of k as the number of moments that may be helpful to describe the law of your system. Okay, so for example, typically if you have a linear quadratic problem, okay, you will be typically equal to 2. So such symmetric neural network has been in fact recently introduced in the literatures, okay, by these authors. And depending on the symmetric operations that you take here, so depending if S, okay, is a max function or a sum function, okay, this neural network are called in the literature point net or deep set. Okay, and so in the same way that you have the approximation capability for feed-forward network, then you also have the approximation capability for symmetric neural network, okay, when the number of neurons m and the number of feature k goes to infinity. Okay, so this is for the symmetric neural network, and now we call that, so which will be used, of course, to approximate the solution to the PDE. And since we want also to approximate the gradient of the solution to the PDE, okay, we introduce what we call capital D symmetric neural networks, which is in fact a neural network aiming to approximate a D exchangeable function. Okay, so compared to the symmetric neural network, okay, what we have in addition is in another argument, okay, here, okay, for the second network psi. Okay, so it's constructed very similarly to the previous one. Okay, and we call such kind of neural network a deep DER set. So DER is for derivative. Notice that an alternative way to generate de-exchangeable function is rather, in fact, to start directly from a neural network in deep set and then use its automatic differentiation. okay, computed, for example, by backpropagation formula in TensorFlow, then if you compute its automatically differentiation, okay, it gives you automatically a D-exchangeable function, and such class we call it AD dipset, AD for automatic differentiation. Okay, so now this slide is to illustrate the relevance for using such kind of symmetric neural network instead of the classical feed-forward network. Okay, and so I give here in this slide, okay, 3 examples. Okay, so the first example here, f here, is an example of a function f which is rather nice, rather smooth. The second one is okay, is much more irregular, okay, due to the fact that here it involves the max of function. And the last one, the third example here, is a function which is quite oscillating, okay, because of this cosinus. Okay, and so what we want to is to approximate. So all these 3 functions are symmetric, and we want to approximate by neural networks either feed-forward or symmetric. Okay, so here is the architecture. Okay, and so the approximation is done by minimizing this quadratic loss function. Okay, by training simulation, by using training data from Gaussian random variable. And so we apply, okay, a gradient algorithm, and we stop the iteration when the error, okay, is below some level, okay, which is chosen here equal to 10 power minus 5. And the maximum number of iterations, okay, we use is 1000. Okay, and so here are the results in this table. Okay, and so let us first look at the first example. So this example f here, this nice function. And so we see that if we use, we try to approximate such function by a feed-forward network, okay, in order to achieve an error of 10 power minus 5, okay, we need 992 iteration in the Adam optimizer. While if you use a symmetric neural network with a deep set, with okay, you only need 5 iteration. The second example, this example, which is quite a function f, which is quite irregular. Okay, so you see that here in this case, the feed-forward neural network does not succeed to approximate well this function. Okay, because you see that using 1000 iteration, the error is very high, and not surprisingly, you see that between the point net and the deep set, okay, it's not surprising that the point net, which is I will call it the symmetric neural network using the max operation, okay, allows, okay, to obtain this this accuracy. And finally, the last example, okay, which is this cosinus example. Okay, and so you see that okay, with feed-forward, after 1000 iteration, you do not succeed to achieve this level of error, but only this 0.0012. While by using okay, deep set, okay, you are able, okay, to achieve okay, 4.10 power minus 5. Okay, so in this example, okay, it's important to illustrate that using symmetric neural network, okay, it greatly improves the accuracy of for approximating symmetric function, and in fact, it may be in fact very crucial, because in some example you see that feed-forward would not be able to approximate correctly the function. And so this means that when you want to solve PDE, okay, so typically if you do not approximate well the terminal conditions, okay, then the error will propagate at any time in your scheme. Okay, so now, okay, now that I have introduced this symmetric neural network, so now we can apply the methods that have been designed for solving PD. Okay, and so here I will use the method that we have developed with Comuré and Zaivarin, so in a paper published in Mathematics of Computation, so which is called a deep backward dynamic programming scheme. And so the idea is the following. So you have some PD, so in dimension D. Okay, so we know that such PD can be represented probabilistically in terms of a BSD. Okay, so BSD means that you have some forward process X related to the linear part of the PD. Okay, so the nonlinear part of the PD is expressed in terms of the generator H. Okay, and so you have to find Y, so the solution to the PD, and Z, the gradient. Okay, solution to this BSD. Okay, and so the starting point of the scheme, is first to discretize. Okay, so discretize in time this BSD. So it is a BSD. So we start from the terminal condition of the BSD of the PD. Okay, and then you just apply a backward Euler scheme. Okay, which means that if you know the value of the PD at time tk plus 1, okay, what you need to compute, is a solution Y at time tk and Z at time tk, so that you you match your BSD scheme, Euler scheme. Okay, and such BSD scheme suggests quite naturally the deep backward scheme. Okay, so which works as follows. So you start from the terminal condition, and then you proceed in a backward induction as follow. Okay, so at time tk plus 1, you have already an approximation of the solution to your BSD or of the solution to your PD. And then, you simply want to minimize over a neural network. Okay, so neural network over for approximating Y and Z by minimizing, the loss function, which is the difference from the Euler scheme. Okay, and then the solution to this loss function, is called Y. So it gives you output. Okay, so the solution at time tk, and then you proceed in a recursive way. Okay, so you see that compared to, for example, to the scheme of the deep BSD scheme of Jensen and E and An. So here we have a local minimization because you proceed in a backward way, okay, with some local minimization. And so so it means that, the number of parameters, of course, less important than if you minimize over the whole neural network in a global way. Okay, and so now if we apply this scheme to our context, okay, so to our context means that now the forward system to be trained, is a particle system of Marquardt of the mean field SDE. The network that will be used to approximate the solution to the PD will be a deep set. The network for approximating the gradient, is AD deep set, automatic diffusion deep set. And then, since we want to approximate the solution on the Wasserstein space of probability measure, of course, what is important is the fact that the training has to explore well the Wasserstein space. Okay, and so for this, an idea, is to when at each time you minimize your loss and train with your Martin-Mazurov SD, we want that our empirical measure explore sufficiently well the state space, the Wasserstein space, and so for this, in fact, what we do is to initialize okay, our process with a mixture of Gaussian distribution in order to explore the Wasserstein space. So here, this scheme that I just described is done for a semi-linear PD. In fact, it can be extended to fully nonlinear PD, okay, by applying a version of the scheme to fully nonlinear PD. And so here, the key difficulty is in the approximation of the Hessian. Okay, and so this is done in a paper which recently appeared in the journal SNPDA. Okay, so now to conclude, let me illustrate okay, the result. And so for this, I will okay, illustrate on a very now well-known example, okay, borrowed from the paper by Carmona, Fook, and Sun. Okay, so it's a paper, it's about a mean field control of systemic risk. Okay, so what is this model? So you have a control Markin-Basov dynamics, okay, where the drift, okay, is okay, the control drift, okay, depend on the law of the process via its expectation. Okay, and so the aim of the social planner, so social planner should be viewed as a central bank who can borrow or lend a rate to different banks. Okay, and so the aim of the social planner is to push the drift, okay, of each banks, okay, close to the average of all the other banks. Okay, and so this is okay, the role of this running cost. Okay, and so in this case, okay, the corresponding mean field control problem or Markin-Basov control problem lead to a semi-linear PD, where the Hamiltonian, integral Hamiltonian has this form. Okay, and why this example is often chosen, because it's in fact it is a linear quadratic Markin-Basov control problem for which we have an explicit solution, and so we can compare our result with this explicit solution. So in this example, okay, so we choose for training data this particle system, which is not really a particle system, interacting system, because here the drift is simply zero. Recall that we have this B term in the choice of the trained data. So B here is equal to zero because essentially for the optimal control, okay, the optimal control makes in fact the drift almost equal to zero. And so it's quite natural in this case to take a drift B equal to zero in order to be close to the optimal control West process. And so it will be better to approximate well this the solution. Okay, and so here are the result. So where we vary both the number of time steps in the time discretization and the number of particles. And so we apply our scheme over 10 independent runs and compare the average value and the standard deviation. And so the last column, okay, represents the relative error with respect to the explicit theoretical solution. Okay, and so as expected, so you see that, okay, for fixed number of time steps, when you increase the number of particles, okay, you decrease the error. And also when you increase also the number of time steps, okay, you also decrease the error. Okay, and so here we see that it's okay, we are able to achieve quite a good approximation, okay, with this symmetric neural network. Okay, and so another illustration is, and also another output of the scheme is the fact that we are also able to approximate the Lyon's derivative, the lift derivative of the solution to this PD. So in this example, the Lyon's derivative is explicit, so it has this form, so it is linear with respect to x, and it depends on mu through its means. And so in the following graph, okay, we plot the solution obtained by the scheme, the machine learning scheme, compared to the explicit solution. Okay, and so in orange at different times. So in orange, okay, it is the explicit solution. Okay, in terms of x. So in terms of x, it is a linear. Okay, and so the intercept represents the average of mu. Okay, and so you in blue, okay, you see the result obtained by the machine learning scheme, and you see that it okay, it quite rather well, okay, the explicit solution. Okay, so I have another example dealing with a mean variance portfolio, which in fact leads to a fully nonlinear PDE, but probably I do not have time, so I will go directly to the conclusion of these talks. So, so what are the contribution of this work? So first, we provide a particle approximation of the mean field PDE. Okay, so meaning that we provide both a rate of convergence, okay, at least in the sublinear case, for both the solution to the PDE and its L derivative. From a numerical methodology, okay, the main contribution or the main novelty in fact is to use, okay, the symmetric neural network, and we have shown that it is in fact very helpful to in this context. Okay, so we are with different kind of symmetric neural networks, so deep set, automatic diffusion deep set of deep DR set. From a theoretical point of view, so here we provide the error analysis in terms of the number of particles, but the analysis could be also completed with a time discretization error. So in other words, where you have a balance between the number of time steps and the number of particles, which can also complete with generalization, in other words, statistical and optimization errors, okay, that have been which is also, of course, important, okay, when we want to analyze completely this error. So, for example, I should mention recent work by Arnulf Jensen and also Mette Zonder and Max Reppen. And there is also another type of error which occurs in our context is error due to the symmetric neural network. For this, up to the best of our knowledge, there are very few results when you approximate a function with a symmetric neural network. Let me, however, mention some papers by Wagstaff and Blom-Brady and T. Okay, and to finish, so here I try to show you how a symmetric neural network can be useful to for solving a mean field PDE, but in fact, beyond this important example of mean field PDE, okay, in fact, using a symmetric neural network may be also quite helpful when you want to solve, say, some class of PDE which possess some invariant permutation structure. So you may think, for example, to PDE which arise in cosmology or in quantum mechanics. Okay, so I think I will stop my talk here. And I thank you for your attention. Thank you.
Many thanks, Huyên, for your great lecture. Do we have some questions?
Arnulf, can I ask a question just like that, or?
Yes, go ahead, please.
Hi, this is Mette Zonder. Hi,
hi, Mette.
Huyên.
Yeah,
greetings from Princeton. And it's wonderful to be able to listen a talk 1,000 miles away. Thanks a lot for a wonderful talk. I have one question about the time discretization. In the very first example on mean field games, the example from the quadratic example, you took capital T equal to 1, if I remember correctly, and then you had 15 discretization points and then 30 discretization points. Yes. And you got a very good approximation.
You mean the table I give for the systemic risk?
Yeah.
Okay.
Yeah, it is extremely good, right? So if I were to, I mean, I don't know, in all problems, 30 time steps would would do the job for me. So if I had to increase that, would that be a problem of some sort or not? What is your experience on that?
If I increase, you mean the number of time steps?
That's right. That's right.
Yes. So in fact, I think we go up to 50, to number 50. So but it increases slightly the result, but because here we already have a quite good accuracy, so we didn't really try to go further into the number of time set. But but for 50, there is no computational problem when implementing the algorithm.
So you think that in other problems, when I can just read this scales with the time steps well as well. It scales extremely well with the dimension and everything, and the symmetric network that you did. I'm sure that it's going to be extremely useful in some financial examples where you have a max or things like that.
Yes. Indeed, when you deal with a max function, or it's but okay, you need some. In financial problem, okay, it's useful when you deal with option with max, but also the asset should have some exchangeability property also, because you need to keep also symmetry also on the generator of the PD, not only on the terminal condition.
Thank you.
Well, Arnold, I cannot hear you for some reason. You don't seem.
Sorry.
Okay.
Another question we had from Sumant Kumar was how you initialized the weights and biases in the training of your neural networks.
How you mean when I applied yes, so I have a slide for this. Well, so when we apply this algorithm, okay, so it means that okay, you need to to solve to minimize several gradient algorithm. Okay, so the key point, in fact, is to approximate well at the first step. Okay, so you start from your terminal data G, and then at time nt-1, what you need is to approximate very efficiently your solution. So for this you need to use a quite number of iterations. But once you approximate correctly at the first step, then at the next step, so with the idea that if the time set is sufficiently fine, so it does not vary a lot, then you can use, in fact, the parameter of your previous iteration as the initialization parameter of your current gradient algorithm, which means that in this case, you only need to use maybe 5 iterations at the other step. So for the first iteration, nt-1, you may use, I don't know, 1,000 gradient iteration, but at the other step, at the other time step, relying on the previously computed parameters, you only need to use maybe five gradient iteration.
And in the first step, how did you initialize? Yes, like maybe with random, some uniform distribution, or
yes, we use yes, it's random. It's done by randomization.
I have also one question, Huyên, was like for your symmetric neural networks, you showed impressive numerical simulations results that they work very well in high dimension. Do you also thought about proving some results about high dimensional approximation capacities of symmetric neural networks, that if D is very large, that they need only polynomially number of parameters in D or something like this, an approximation result of this kind. Have you thought about that?
Yes, so of course it's a natural question. So so we have not thought about it. I guess that we should obtain the similar result than for what we get with feed-forward networks, so the same polynomial dimension. But as I said, to the best of my knowledge, there are in fact very few theoretical results, even for the approximation capability of the symmetric neural network. So, for example, so for feed-forward, you have this convergence result due to Francis Bach, okay, which says how you approximate well a function in terms of single layers. But I think there is no counterpart when you deal with symmetric neural network. So for me, it's still an open question. So as I said, there's some work we more or less are interested in this direction. So I cite this paper by Wagstaff and Blom, Reddy, and Tay, but it's only partial results.
Many thanks. Do we have any other question? So if this is not the case, then let's thank Huyên once more for his great lecture. And yeah, there will be a next talk by Ethan Taskmore in the next week. Okay. Thank you.
Okay,
bye-bye.
Thank you very much.
Thanks a lot to both of you. Thanks a lot.
Bye-bye.
Bye-bye.
Okay, bye-bye. Thank you.